All right, hello everybody. Today we're going to do a deep dive into Node streams. We're going to talk about both streams and web streams. Good morning. Like she said, my name is Ethan Arrowood, open source contributor and senior software engineer at HarperDB, a distributed real-time application platform. That's me and my dog. We just finished an 8-mile hike really, really high up, and he wanted the enjoyable ride down the mountain. So, what is a stream? A sequence of data made available over time rather than all at once. There's some key characteristics we'll go over: memory efficiency, finite and infinite size, sequential access, and real-time processing. So going into the first one, memory efficiency, you only need to hold the current chunk in memory. Looking at the examples at the bottom, in a traditional program or a non-streaming program, you might have to load your entire file into memory to do anything with it. But with a streaming program, you can actually take one chunk at a time of different sizes, process just that chunk, and then get rid of that chunk when you're done. This allows your program to use significantly less memory than different ones. Sequential access is kind of simple. Just think of it like a conveyor belt. The data comes in over time, kind of in order like the diagram shows. Dynamic size handling, this is the finite infinite, which is really just that you don't need to know the total size up front. The application can even have an infinite amount of data. So in this diagram, the application is streaming logs. Think of it like a production system. Those log chunks are going into your application, which is a processing stream, and that processing stream is generating, something like a log entry, and you're writing that log entry to a log store. The idea is that those logs may never end, and your log store might grow infinitely, but your processing stream only has to hold on to those couple of chunks that it needs at a time to create that log entry. And then last, real-time processing, probably one of the most important features of streams is that you get to start work immediately. This is very good for efficient programming. One of the examples I like to call out is like browsers and the time to first byte system, where with a really large web page, as soon as that first chunk reaches the browser, it can immediately start the expensive work of rendering that page on the client. That's your time to first byte core web vital. Then the rest of the chunks of that page can continue to stream in, and the rest of the page can get rendered. And we'll kind of go back to this example later when we talk about React streams. Some additional examples include standard streams, file streams, media, network streams, and the classic is video streaming. I picked YouTube, but like any live stream or any video streaming service on the internet, you don't need to wait for your full video to download. You click the video, it starts playing, and then you only are processing the current chunk of frames that you're watching. That's why when you're on poor connection, sometimes you'll see it buffering. It's kind of still downloading even those chunks. Your network is so slow it can't even handle the data of the current sites you're looking at. But also it means when you click around a video real fast and try to skip around, you still get some of that buffering, because in that scenario, you've kind of interrupted the streaming. You're asking for it back in time or forward in the future, so it needs to kind of make a request to that moment in the video versus just watching it continuously. And lastly, live streaming. Go back to that example of infinite size. You could be watching a live stream that never ends, and your browser doesn't crash, your browser doesn't blow up with memory. It can continue to show you that video that never ends. And that's kind of the benefit of streams. So once again, streams are ideal for large files, network communication, real-time data, and limited memory environments. And I keep calling out browsers because we've all known how much memory Chrome can use. So going into some of the lower level now, Node.js streams added way back in 0.9.4. I'll be using the color coding, the blue text to kind of indicate Node streams today. Those are Writable, Readable, Duplex, and Transform. They're all instances of event emitter, And they're used throughout so many other Node.js APIs. File systems, requests, standard streams, TCP, zlib, crypto, they're everywhere. The Node.js WebStream API, we're going to be using orange, or however this might be showing up on screen, kind of a yellow. That's added in version 16.5 and was no longer experimental in 21. This implements the WhatWig stream standard, which is like the browser thing. This is the standard API for streaming data across JavaScript environments. That's kind of, I think, a quote from MDN. There's been talk about what really means for something to be a standard, but the idea is at least that with web streams, they are what's used in the browser. It's what kind of backs fetch, and it's what kind of is implemented across many different JavaScript runtimes, if not Node streams. And those classes are Readable Stream, Writable Stream, Transform Stream. And lastly, web streams are used in Node where they are expected to be, but not really anywhere else. Meaning, like in text encoder stream, which is a web API that's implemented in Node, web streams are used. Fetch, web API, web streams are used. At a high level, this is kind of a brief overview. Node streams has been around a lot longer and has had a lot more experiments, I guess, thrown at it. It already has async iterator helpers, which is now a stage 2 TC39 proposal. So web streams, or sorry, we'll take one step back. Node streams and web streams are also async iterators. And so, or at least the readable ones are. And async iterators, just like iterators, can have like helper methods, map, filter for each. Node has those helpers already because they were added before I think the proposal was even sent to TC39, but now there is an official proposal to get those iterator helpers onto web streams. Web streams won't have those even in Node until they're added to the spec. Quick language clarification. I'm trying to keep things specific here. Programmers like that. Node stream, again, blue. The classes omit the word stream. This is how it is in the source code. Web stream classes include the word stream. So if you see things written as readable, that's Node. Readable stream, that's web. But even Node web streams refers to the Node implementation of web streams. It still uses that same naming convention. Also, if a space is used, like readable space stream, it refers to the higher level concept, so it probably includes both readable and readable stream. And these are not universal rules. These are things like I've kind of made up and I use when I communicate about streams, so your mileage may vary in the wild. Lots of text. Really the first API style is the one I think that I'll call out the most. Events and callbacks for Node Readable and async iteration. On web readable stream, it's promises and async iteration. And then looking at some code, which I think everyone will be a lot more grateful for. On the left-hand side is how you would instantiate a readable. There's a construct method. There's a read method. This is kind of your key, your mandatory one. This is where you would retrieve data from the underlying source, and you would use the this.push method to kind of push that into the queue for that to then be read from when it's consumed. On the web readable stream side, it's the start and pull method, which gives you a controller, and you would do controller.enqueue that chunk for a similar effect. And for reading, I could spend a whole nother 30-minute talk just talking about the different ways to do readable, like process Node.js readable streams. But the gist is that there's a flowing mode, which has like you use the onData method, or you can use the async iteration for a wait chunk of R. Or there's pause mode, where you need to call readable.read manually and verify the output of that before calling it a second time. Things are a lot simpler on the web. It's all promise-based. You get the reader from your stream, and you call reader.read, and you await it. Or you can just iterate over that reader itself. Writable is very similar. On Node side, it's events and callbacks based. On the web side, it's promise-based. And the creation is similar as well. There's the write method, which is the core piece here. Node.js has a write_v method, which allows you to process multiple chunks in one request or batched. Writable stream on the web side has start and write as well. Has that controller in there to do the controller work if necessary. And then writing in Node, I use this code example from the Node docs directly. Again, this has to do with kind of the back pressure and the managing the internal queues. Stream.write, the inside of that if block, that's your your key there. It returns a Boolean whether or not you can continue to write. And you have to kind of honor that, because otherwise you might overflow its internal queue and not really respect the back pressure. So if that returns false, you have to wait for the drain event to then continue writing. Otherwise, you can, if it returns true, you can continue writing, which means the internal queue is not full yet. Again, like, could spend 30 minutes talking about the internals of streams, Node streams themselves, let alone web streams. Web streams are, again, very simple, promise-based, get the writer, await, writer.write. Duplex and transform streams. There is no duplex in web streams. There is just transform stream. But in Node, transform is a duplex stream. Duplex is an instance that implements both read and write. And the difference in Node.js is that a transform stream in Node only has to implement the transform method instead of implementing read and write. And the idea is that the inputs are related to the outputs. There's no requirements that they must be the same size, produce the same number of chunks, or arrive at the same time. But the point is that you get a chunk, you process that chunk, you create some output from it, and you move on to the next one. With just a duplex stream, you can get a little more creative. But then the key difference between transforms is that in Node.js, a transform is an implementation of both readable and writable. So if you do instance of, you can do transform instance of readable. It'll say, yeah, true. Transform instance of writable, also true. And it has all the methods, t.write, t.read, or t.onData. You can also async iterate over a transform stream. On the web side, it has properties, readable and writable, which then you just use like the instances that they are. Get the reader, get the writer, and do your things. Under the hood, the way the queues are managed are a little bit interesting as well. But that's kind of the gist, is that a transform stream on the web is not an instance of a readable stream or a writable stream. It has them kind of inside of it. Quick note on performance. You've heard it before at this event. You've heard it on social media. You've heard it at other events. Micro benchmarks really aren't that important. Just to be frank, I could sit here and tell you and show you how if you create 10,000 web streams very, very quickly, that is slower than creating just a writable. But inherently, that's true. They're promise-based. There's a little bit more asynchronicity to those things. That's just kind of unavoidable, no matter how much you optimize it. But also, it's almost a marginal difference. The real thing that matters is that you profile and fix the slow parts of your application. And that kind of comes to the bottom code. I'll kind of skip ahead, is that if you have really expensive operations in the utility and the operation of your streams, that's going to be your performance benchmark, or sorry, your performance barrier, not the stream instance itself. You can pick web or Node. They'll both perform probably the same. But if you still have a really expensive operation for your sources, that's just going to be what's impactful. And I'll also note that interop can be a little bit expensive, just because it's also expensive and also maybe a little bit dangerous to get it just right. So I tend to try to pick one node or web and stick to it, or find a point and do one interop and then stick with the new version as long as possible. Speaking of interoperability, there are 6 experimental APIs in Node to kind of switch between the two types. You can do readable, writable, and duplex from and to web. There's not much else to say there, but they are experimental, so do note that. And let's finally dive into our first example. So we're going to be going over a live reload server. When I was creating this example code, I wound up having this crazy amount of slides, and it turned out that 10% of it was actually streaming. So I threw it all out, and we're going to talk about a diagram real quick to kind of get the gist of what it is, and we'll take a look at the streaming part of the example. And we'll move on to the next one. So on this actually starts at the top right of the diagram. On the server, your file watcher starts watching the file system, and then fast forward to your client makes a request for a page. Your static handler will then retrieve those page contents from the file system, and then when it gets that file, let's say your index.html, we're going to inject that page with your live reload script. That live reload script utilizes WebSockets to create a connection back to that server, which happens next. So on page load, you create a WebSocket connection. That WebSocket connection then creates a listener on the file watcher. When the file watcher detects a change in the files, it signals the WebSocket handler to send a reload message to the client, and then the client can reload the page. And that is the gist of how all kind of live reload servers work. When it comes to frameworks with hot module reloading, it's a little bit more nuanced, but this is the gist. And it's not that hard to build yourself. So it really just starts with a transform stream. Sticking with encoded text so we don't pay the penalty of going back and forth between UTF-8. At the top of the page, we're looking for the end of the HTML block. And in our transform, the first line, const I, chunk last index of, you're looking for this uint8 array inside of that chunk. If that exists, we're going to create a new chunk, which is just a buffer of the length of the chunk plus our live reload script. And then we're going to inject that live reload script right before the end of our HTML tag, because this really is just a script tag with WebSocket stuff in it. And then we use the callback to send that injected chunk back to our stream. And if you don't see this closing HTML tag, you just return the chunk as is. You don't do anything to it. So it's really efficient. And if you want to see this all live, check out this repo I have, Live Reload. It's got a couple other stuff in it. This is just something I've played around with, not a real serious application here. Use something else. This is more just for demo purposes and learning. But it's built on Fastify using Fastify Static, WebSocket plugin, and Watcher. And it leverages the onSend hook to kind of pull it all together, where with onSend, again, this code snippet's also simplified. If the payload is a readable and it is like the page and it's non-cached and things like that, then we just pipe the payload through that injection transform, and that payload in this onSend hook is your HTML document. So all it is a stream itself of chunks, and you can call pipe, and this is really efficient for creating that full live server reload loop. Moving on to a next example, React rendering streams. We won't go too much in detail here, but taking from the React docs, you can see on the left-hand side the node stream, which is render to pipeable stream. The format of this is very interesting, but they have this callback on shell ready. And when this function is called, that's when you're going to want to pipe your response to your React. You use this pipe method that is returned from render to pipeable stream, and you then pass your destination stream to pipe, and it will push along the React chunks. And the similar thing is on the right-hand side, except you don't have to do the on-shell ready part. You can just use the return stream. This is what enables the suspense boundary system and partial page rendering, which are like some new React features. Many other modern web frameworks have this as well, and it's really exciting. It's enabling the fact that a page not only can start loading early, like the earlier example of time to first byte, but also that you can have parts of your page that take a lot more time to load than others. Your page can show up, be fully functional within a few milliseconds, and then the rest of the slow parts can continue to load in over time, and you can provide kind of fallback things, shimmer for images, stuff like that. Last demo, and this is going to be HarperDB focused, we're going to be looking how to leverage what we call our eager query response system. So I'm going to jump over to a code editor real quick, and we'll kind of walk through things. I'm going to make this a little bit bigger. Okay, so there's a lot going on in here. To start off with, I don't have enough time today to do a full HarperDB demo. There's a ton to HarperDB. But to give the high level, we are going to be using a HarperDB component. And all a component is basically a JavaScript project. We have a very simple package JSON. We are using ESM today. HarperDB's config system, config.yaml, put it in your root and call it a day. We're enabling the REST component here. This will do automatic RESTful API generation. And then we have GraphQL schema. This will define our tables. And then the JS resource API. This is kind of the magic code. This is how we're defining our document. We're creating an items table. Has ID, name, price, and quantity. We use GraphQL to do that as a utility, but you can also do this through other methodologies. This is a seed database. The items here are really simple, just items in your like a grocery store. And let's pretend that we need to find all of the items that have a quantity greater than 10. Well, in this, we're using an async generator, the sales item generator function. This starts by doing the query, and then the query here is going to return all items in the items table that have a value or a quantity value greater than 10. We can iterate over this query itself as an async iterator. And for every one of those items, let's pretend we have to do something really expensive. In this case, we're calculating the sales price. We're also going to put in a set timeout here, just so it's a little bit more obvious. But you could think of maybe you're rendering a page, or you're doing a very expensive data calculation. And maybe your query is a lot more complicated. Maybe the query itself takes a little while. And also, maybe you have thousands on thousands of return values, and so you need it streamed in. You can't handle the entire response all at once. So here, we're going to iterate over the results of this query, and we're going to yield them one at a time. In HarperDB, in a HarperDB resource component, all you have to do is export this class, sales items, which extends our global resource. You provide a get method. That get method can return any kind of async generator, and that means that you can use a readable stream here, and it will work just the same. And putting it all together, if we run HarperDB start, you'll get our cute dog. And then, if I get this right, we're going to curl using non-buffering mode. We're using the REST API endpoint, which is auto-generated for any exported resource classes in HarperDB. The sales items class we defined just above. And if we run it, we'll see that it is now streaming back responses every 3 seconds. And this demonstrates the fact that the query itself is processed over time over all of the chunks. And this only scratches the surface for what's capable with HarperDB systems. So if you're interested in learning more on HarperDB, let me know. I also have some really fun stickers, so find me after the talk. I have some extra resources here about streams. I highly recommend checking them out. And with that, thank you so much. I really appreciate you all taking the time.